Hello everyone, welcome back. This is 1-9 Basic Circuits, Logic Gates, Flip-Flops, and Latches from the Compact Redstone series. I'm Amy222, and today I will talk about some logic gates, flip-flops, and latches that you find useful in some of your logical circuits, or perhaps if you want to pursue your further knowledge in computational redstone, this is going to be a basic video to help you consolidate the necessary knowledge for it. So without further ado, let's get started. I will start on talking about logic gates first. So let's talk about the most important or the most basic logic gate, which is a NOT gate. So say if you want to invert a signal, so if you have a signal of 0, then you want to invert it to 1, and if you have a signal of 1, you want to invert it to a 0. So how will you do that? The natural method of doing this is using a NOT gate, and in Redstone, the most simple one to use is a Redstone torch. So if I have a input of 0, then the output should be 1, hence the Redstone lamp is on. And if I have an input of 1, then the output should be 0, hence the Redstone lamp is off. You can alternatively say that when the input is false, then the output is true, and the input is true, then the output is false. And notice that you can always mutually say between 0 and false and off versus 1 and on and true. Basically, all of the three terms can be used mutually. So it's important for you to know. So basically, 0 off or false versus 1 on and true. All of the three terms basically represent the exact same thing. So this is the most simple logic gate that I have. It only consists of one input. So let's consider two inputs now, because we have a lot more interesting combinations with them. I will only talk about the two input cases. For inputs more than 2, then that is not included here for simplicity. So here I have an OR gate. OR gate is basically, say this input is A and this input is B. If A is on or B is on, or both of them are on, then the Redstone lamp should be on. This is an OR gate, because you basically want, if one of them or both of them are on, then you should have the output on. That's the meaning of OR. So here, on, both of them on, one of them on, none of them off. And yeah, again, Redstone dust is the most basic form of an OR gate. However, if you are more interested in electronics, then you would think that this OR gate isn't exactly the best representative way of an OR gate, because an OR gate should be a diode instead of a transmitter, a two-way transmitter. So you only want one-way transmission. And that's why you can use a repeater here instead to disallow transmission from the other way. So say if I have a Redstone dust here, it doesn't transmit back. Whereas if you use a Redstone dust, it will just transmit back. And this doesn't really make sense in electronics. So instead you can use a diode if you want a more representative way of showing an OR gate instead. But yeah, that is just some personal preferences, let's just say. So yeah, don't mind about that. Okay, let's move on to another circuit or logic gate, which is an AND gate. So using only NOT gates and OR gates, we can already construct an AND gate, because there isn't really any Redstone components that itself is an AND gate. So we need to make some circuits based on OR gates and NOT gates to construct an AND gate instead. So what exactly is an AND gate? If only both of these levers are on, then the output should be on. If only one of them are on or none of them are on, then this should be off. So you can see this works like so. So how do you represent an AND gate? Well, this is the logical representation, which is basically say this is A and this is B, then not A or not B, and you inverse the entire signal with a NOT gate again. So not open parentheses, not A, or not B, close parentheses. Then this itself is exactly an AND gate. So yeah. So these are the three most basic logic gates, and you can basically work around with just simply these three logic gates already. Actually, only two is enough, to be honest. OR gates and NOT gates. Like, just having these two are enough, because AND gates literally just a combination of NOT gates and OR gates to construct this. So yeah, two logic gates is already enough for it, and your entirety of logics. However, there are also some other logic gates that would be useful for us to implement and to simplify our logical representation. So I'll just introduce them as well. So here, this comparative thingy is called an exclusive OR gate. Now, some people might say it's an XOR gate or XOR gate. They all mean the same. Exclusive OR gate. So what does an exclusive OR gate does? Oh, sorry, what does an exclusive OR gate do? Then it's actually quite simple. So you only want to have the output to be on if either lever on, not both. So if one is on, it's on the output. And if both are on, then this should be off. One of them on, none of them on, off. Simple, right? Let's just see what this comparator actually does. Notice that these are in subtraction mode. So when I have this to be turned on, this has a 15 signal, this has a 15 signal, this has a 14 signal. So this comparator would be off because 15 subtract 15, 0. But this is 14, subtract 0, 14. So it's on, lamp is on. If both are on, then all of the four does emit signal strength of 15. 15 minus 15, both of them say 0, so the output is off. And if, again, one of them is on, then it's just exactly the same thing, but mirrored. And both off, then it's off. So this is what the comparators are basically doing. Now, you can actually use dust and torches to make an exclusive OR gate rather than using comparator logic, which is actually in the exercise here, so you can try it yourself. It's actually a very conventional logic gate that some of you might already know before watching this video, but I'll just leave it to you as an exercise in case if you want to try it and have never seen the logic gates before. Now, another way of representing exclusive OR gates is actually using sticky piston and block splitting and using observers. So yeah. Again, if one of them is on, then it's on. So both of them on, then off. Again, on. And then none of them, then off. You can already see why this works. It's just basically pulsing the sticky piston with a 1 tick or 2 game tick pulse such that the block splits. And yeah. However, you might also see one of the disadvantages or some few disadvantages of using this design. First of all, it's on a pulse base, so if you have this input and this input simultaneously turning on or off, or if they are literally 2 game ticks apart, then you have a problem because this sticky piston is not going to block split as you expect it to, or if both of them are simultaneous, then it will only do 1 pulse. So both of these situations, it will break. The second thing is that the use of moving components is not really that practical in computational redstone, basically. You would have noises, and especially for pistons, they have quasi-connectivity, so if you have something that powers above them, you will have big trouble. So usually people don't use that, but hey, it's still just a way of implementing exclusive OR gates. And using this is much more preferred, because you do not have to restrict how you power the inputs or restrict the delay between the inputs, which usually is not really that possible. Although there are some other circuits there in the back there to help you to regulate between these two inputs, or the delay, I should say. But then I will not talk about the details on how to implement this. But yeah, anyway, this also just shows why this is more handy than this one. So anyway, now that we know the basic four, basic four, the NOT gate, OR gate, AND gate, and exclusive OR gate, what if we try to invert the output signal then? Well, here comes the first one, which is a NOR gate, which is just inverting the output of a regular OR gate. So for an OR gate, you will have the lamp turn on if either levers are on. So here, if we invert it, we mean that when either lever are on, then this output should be off. So here, off, both off, one off, none on. So yeah, this is a NOR gate itself. And the second one would be a NAND gate. So instead of having this torch here to invert it, we just omit it. Omitting the torch and immediately inverts for us. So only both of them are on, will this be off. And if only one of them or none of them, then this will remain on. So NAND gate here. And finally, we have exclusive NOR gate. So again, we just invert the inputs. So on if one of them, then off. Both of them on, one of them off, both of them on. And the same thing happens when you use the block splitting mechanism, except we just have these redstone blocks to be outwards, not inwards. So one of them off, both of them on, one of them off, both of them on. Sorry, none of them on. So yeah, you can see that by just adding an inverter to the outputs, then you automatically have yourself these logic gates. So the first property is literally that. NOR, NAND, and exclusive NOR gates are essentially OR and exclusive OR gates with outputs inverted by a NOT gate, respectively. Now, besides this a bit more intuitive and trivial property, there's actually one more property about these logic gates when we are talking about two inputs only. Which is that, what if instead we invert the outputs of the logic gates, we invert the inputs of a logic gate? Okay, let's just see what happens for NOR gates then. So a NOR gate looks like this. And let's consider an AND gate. So AND gate looks like this. So what would happen when we try to invert the inputs instead? Then what happens to the AND gate would be this redstone torch will be replaced by a bust. This as well. So see, they are exactly identical to the NOR gates. So we can conclude that NOR gate is basically an AND gate with the inputs inverted by a NOT gate. Sorry for the ambulance noise, someone needs help. So anyways, let's consider NAND gate here. Oops. An AND gate looks like this. Then what about an OR gate? An OR gate looks like this. What if we try to invert the inputs of an OR gate then? Well, this dust will be turned into torch, this dust will be turned into torch. Then we see equivalency. A NAND gate is literally an OR gate with inputs inverted. And similarly, you can also prove that the same for exclusive OR gates and exclusive NOR gates. It works exactly the same. So yeah, basically the property is saying if you invert the inputs instead, then you can match NOR, NAND, and exclusive NOR with AND, OR, and exclusive OR. So yeah, these are the two interesting properties. And before I move on to flip-flops and latches, let me introduce you one more less common logic gate, which is called an imply gate. This is an imply gate. What does it mean by an imply gate then? Well, imagine when you say A implies B. What you're meaning is that the output is only true when A is on, then B must be on. So the output is only false, or the logic is only false, when A is on and B is off, because A does not imply B. However, when A is off, then no matter B is on or off, A implies B will always be true, because it's just null for A. And whether B is on or off, A implies B will still be true. So, hence A implies B. So, let's just see the representation here. So, only if A is on and B is off, then A implies B is off. So, yeah, there you go. B is on. A is on. So, A is off, B is on. Both of them are off, then still on. So, yeah, A implies B. So, you can also see how it is really represented with OR gates and NOT gates. A implies B literally means B or not A. Literally. So yeah, this is a NOT gate, this is an OR gate, done. So imply gate. Good. Now that we know the basics of logic gates, we can move on and talk about flip-flops and latches. Now, what are flip-flops and latches then? Well, here comes a few definitions that you might think is confusing, but after I go through the examples, hopefully you'll understand it more. So, latches and flip-flops, they are memory devices and are implemented using a bistable circuit. What is a bistable circuit then? It basically means that the output will remain in either 0 or 1 state. So either it's on or off, or either it's true or false. Only one state or the other. Nothing else. This is the first definition, but it still doesn't really tell you the difference between a flip-flop and a latches. So here comes the second definition. So flip-flops have an extra clock or gating input added to a latch circuit. And what does the clock inputs do? It basically prevents the circuit from immediately processing the inputs and waits until the clock emits certain conditions to process instead. So this is the definition that we'll use throughout this video. However, you should notice that the definitions of the differences between latches and flip-flops can have other meanings according to other individuals. And I will introduce you the alternative definition later, because you might need to refer to some online materials and platforms that uses the alternative definition instead. I use this definition due to historical reasons, and I just basically took them from lecture notes in university courses. So, yeah. And before I move on to even talk about the first example of latches, I'll just tell you some basic information first. Since we have the second definition, we can say all gated latches, basically latches with the gating input, are clocked flip-flops, or flip-flops for short, because we have the second definition. Because if you add a if you add a gate input to a latch, then it automatically turns it into a flip-flop. So that's what the second definition is telling you. And you can always define flip-flops as all latches with an additional clock input. Basically, if you see a clock input, it's a flip-flop. You can just say it like that if you want to. And there are 4 basic types of latches and flip-flops. We have SR, which means set and reset. D, which means data or delay. JK, it doesn't really have anything about it. And T means toggle. And below, I will only introduce you the practical ones, which are SR latches, SR flip-flops, D flip-flops, JK flip-flops, and T flip-flops. And let's talk about the final definition, which is edge-triggered versus level-triggered. So edge-triggered refers to a circuit that processes during either rising edge, falling edge, or dual edge. I hope you understand it based on your knowledge from 1-6 pulse signal conversion. And whereas level triggered refers to a circuit that processes during a signal of either 0 or 1. So 0 we call this as a low level, and 1 we call this as a high level. And for all latches, if I say edge triggered or level triggered, it refers to all of the inputs. However, for all flip-flops, then edge triggered or level triggered refers only to the clock inputs. And the remaining inputs are not really important because they are usually predetermined by their levels instead, so either 0 or 1. And the only concerning thing for flip-flops is the clock inputs, because we need to know when the clock inputs will trigger the flip-flops processing. That's the most important thing. So after all of this haywire of definitions, we can finally talk about the first circuit I have for you, which is called an SR NOR latch. It uses only redstone dust and torches. So here I also use target blocks as well, because to simplify things. And if you don't want to use target blocks, you can always have redstone dust on top. So let's just see. I have a reset input here and a set input here. So if I set this, the redstone lamp will turn on. Nice. And then no matter how many times I set it, the redstone lamp will still be on until I reset it. Then the redstone lamp is off. And how many times I reset it, it will still be off. That is what it means for set and reset. If I set it, the output should be on. If I reset it, the output should be off. No matter how many times I set it or reset it, it will still remain its output. That's it. And the same thing goes for here. I'm not going to explain it here. Now, you might be wondering, why do I use a slab here? This is for some more technical reasons that I will not explain it here too much. Because what happens when S equals R equals 1, that's just basically to say for this case. Because it's weird, right? If you try to set and reset a latch, then what it should do then? It shouldn't do really anything, because that's just weird. And in fact, if we have set equals reset equals 1, so if both inputs are on, we actually do not define any output for this case, because it makes no sense. So you should never try to set and reset a latch, in an SR latch, SR NOR latch or SR latch. Never do that. I mean, in redstone applications, you would see some reactions from the actual circuitry, but it makes no sense actually. You should never try to have S equals R equals 1. And that is just to cope with the case when S equals R equals 1 for this slab. You can just replace it with a sine wall if you want to. So yeah. And also this slab also prevents this button from actually powering this lamp, because it actually shouldn't. But yeah, anyways, you can just, it doesn't really matter in your daily applications actually. So anyways, now the second one I'll be talking to you is a rising edge triggered SR latch. Now, if you are careful and listen enough, more carefully enough, then you would realize that I say this as an SR NOR latch, whereas this I said as an SR latch. So what's the difference between them? Let me just build a proper circuit for SR latch actually, to let you understand what exactly does it mean. I'll just use the traditional one because it's faster. There you go. So let me also build the NOR gates back, just to show you what exactly it is trying to do. So this is the NOR gate. Do you see where the NOR gate is going from here? So this dust and this dust both powers this block, and the output is this dust, let's just say. And what is the relationship between this dust and this dust to this dust then? It is exactly a NOR gate. You can literally compare it from here. Dust, dust, torch. Same here. Dust, dust, torch. The OR gate is literally just a block here, by the way. So yeah, you see it's a NOR gate. So this is why we call it an SR NOR latch. Whereas this dropper circuit has nothing related to NOR gates. You don't even see any relationship with logic gates. That's why we don't call it an SR NOR latch, but instead we call it as an SR latch. So this also means that I don't really have the accuracy for one of the circuits that I've mentioned in 2-7 circuits, dropper hopper circuits, where I explained this circuit to you as a RS NOR latch, where in fact I should say it as an SR latch. So you might realize there are some differences. One, I added the word NOR, when in fact it has no NOR gate components. And secondly, I reversed S and R and say it as R and S, which is not really that accurate, because you should always say set reset instead of reset set. It doesn't really make too much sense. But yeah, anyways, this is also telling you that you should be able to understand from others what they mean by when they say RS NOR latch or RS latch, because people don't really have the accuracy for these kind of names. So although you know the accurate name is SR latch or SR NOR latch, but you should still be able to understand when they say RS latch or RS NOR latch, even though when they don't have NOR gate components, or when it should be called SR and not RS. But yeah, anyways, so that's a bit off tangents, but anyways, that is also important for you if you are trying to communicate with others. So back to here. So I say this is a rising edge triggered SR latch. Why do I say it's a rising edge then? Because even though when this is kept as 1, it actually does really nothing. It's actually from the states from 0 to 1 that actually triggers this dropper, right? So if you see that I press these two buttons, then this lamp will be off. It will be on for a brief moment, but it will be off very quickly, because it is based on the rising edge, not the level, aka 1. It's not based on when it's on, it's based on when it's going from 0 to 1. That's the difference. So this is a set, this is reset, and yeah, it basically just does the same thing as an regular SR latch, SR NOR latch, however without the NOR gate components, and it's rising edge. Whereas this one is actually a level triggered, a high level triggered SR NOR latch. So there is an alternative way of doing this, is to do this. Now remember when I say that S and R must not be both equal to 1. Why is this possible now? Well, it's due to the powering properties of droppers that I will explain in 2-7 circuits, dropper circuits again. The property basically says that if you're trying to power with a repeater input, notice it must be a repeater input. If you're trying to power a repeater, if you are trying to power this dropper and activate this dropper, for example, so for this button basically, then it will process this dropper first, then this dropper. And notice that I set this as a rising edge triggered RS NOR latch. Sorry, SR latch. Oh my god, I said it wrong as well. Anyway, so this is a rising edge triggered SR latch. And even though S and R are both set to 1, basically, they do not have the same timing of rising edge for each other. The rising edge for this dropper is ever so slightly earlier than the rising edge for this dropper, even though they're at the same time instant. Like basically their power at the same time. However, the rising edge for this dropper is ever so slightly earlier than this one. So that's why when you see it here, it actually sets instead. And no matter how many times you do this, it will still set. The reason is this dropper is processed first, so it would move its item back down. But then this dropper is processed now, so it will just move it back up. And that's why when you press this button, it will just do nothing. Basically. And same thing for a reset button, except it just reverses its course. So just apply it reversely. Nothing too interesting. So anyways, so that is why you can now set S equals R equals 1, because this is a rising edge triggered SR latch. And remember, you must use a repeater input to power the dropper. And if you use a dust input, it will be locational. Sometimes it would be set, sometimes it will be reset. You never know. You need to know it depend on the location, basically. So after we talk about this rising edge trigger SR latch, we will talk about the other ones using pistons now. So actually a slider is a high level triggered SR latch. So set. How many times you set it doesn't really matter until we reset it, and it will turn off. So high level trigger, because it's dependent on when the piston is trying to power. So if you have a very long pulse here and a very short pulse here, then this would just not respond, actually. So same for here. So S and R, basically. And yeah. Okay, before we move on to the next section, I will talk about two things. First off, I've mentioned SR latches, but then I haven't mentioned about SR flip-flops. That's because SR flip-flops will be introduced together with JK flip-flops. So I will just introduce that later. Second thing is that I should mention T flip-flops to you now. However, T flip-flops, I've already mentioned it in 1-6 pulse signal conversion. There are 8 circuits that you can refer to. However, the T flip-flop designs in 1-6 are not exactly T flip-flops, because for a proper T flip-flop, you should have a T input and a clock input. However, the T flip-flop designs in 1-6 always assume T equals 1, so it will always toggle. Thus, the only input in there is the clock input. So regular T flip-flop should have 2 inputs, but all of the designs in 1-6 only have 1 input, and that is the clock input. And we always assume that when we activate the clock input, that it will always toggle. So T always equals to 1. Always. So that's why you see a slightly different. However, actual T flip-flops, like you have both inputs, input line and the clock line, is actually not that useful compared to only one input where you only have the clock inputs. That is much more useful because you obviously always want to toggle when you power the inputs of the circuits. It is actually very weird for you to not want to toggle when you power the input, or at least that rarely happens for piston doors. So yeah, that's why I introduced the T flip-flop designs to you, where we always assume T equals 1. So yeah, go ahead to watch that video if you want to know more about T flip-flop designs. I will not repeat it here. I'll move on instead to talk about D flip-flops. So whether you notice it or not, you actually encounter a lot of situations with D flip-flops. So for example here, you can use quasi-connectivity because quasi-connectivity requires block updates or redstone updates. And say here, if you power the data line, which we call as D, this piston is never going to realize until it receives a block input or a redstone input. No, sorry, a block update or a redstone update. I'm saying things. So it never powers this redstone lamp, or it never extends until we give a no block update. Whoosh, then it powers. So this is called D flip-flop, or I should say a dual edge triggered D flip-flop, because when the clock input turns on or turns off, so the edge from 0 to 1 or 1 to 0, then it will always update this piston. So dual edge triggered the D flip-flop. It triggers both the rising edge and the falling edge. So D flip-flop. You can also see the reason why this is called a D flip-flop or delay flip-flop, because it's basically delay between the data line, and until you trigger the clock line, the data line never sends the signal directly. So, yeah. Next, we will talk about, instead of a edge triggered D flip-flop, we will talk about a level triggered D flip-flop. This is called a high level triggered D flip-flop. It uses repeater locking. So yeah, actually repeater locking is one of the D flip-flop mechanisms, literally. So if I have D powered here, it does nothing because the repeater is locked. Whoops. But then if I release the clock, or if I turn on the clock, then the data line is going to go through. So now it will respond. Yay. But when I lock it back, so the clock equals 0, then it's not going to turn on or off now. It's going to be locked forever. So yeah, this is high level triggered because we are literally locking the repeater according to the level given. So when the clock equals 0, this is never going to send a signal. So high level triggered, because when we triggered it at 1 high level, then this is now unlocked and the signal can pass through. So high level triggered. So if you try to invert it, by simply this is a low level trigger now. Just like that. So anyways, so we have a dual level we have dual edge triggered, we have high level triggered. So what about only one edge triggered? So let's just see the case for a rising edge triggered D flip-flop, which is actually combining two of them. So you have the data line turn on, let's just say. If we activate the clock, on the rising edge, it will turn the redstone lamp already. Same thing for when turning off. So it's the rising edge, not falling edge. For falling edge design, how will you do it? Actually, it's the same thing. You just invert it. It should make sense for you. So, press the button, nothing happens. Falling edge, it will turn on the lamp. Again, rising edge, nothing happens. Falling edge, it will turn the lamp. So this is the falling edge one. Just inverts the clock input. So yeah. After talking about the flip-flop, let's talk about JK flip-flop. And just saying, a lot of the circuits that I found are actually from the Minecraft wiki. I would give you as a useful resource in the documents below, along with the work download. So don't worry. So this is one of them, along with many others actually. So this is a rising edge triggered JK flip-flop using an SR NOR latch. So basically here, you already see it, SR NOR latch here. And an inverted rising edge monostable circuit. So here, this is inverted. I hope you understand why. Try to apply your knowledge in 1-6 pulse signal conversion. Okay. So yeah, let's just see what happens when we try to use the JK flip-flop. If J here and K are both set to 0 and we rising and trigger the clock, then nothing happens because so no matter how many times you press the button, nothing happens, really. But if J equals 1 and K equals 0, then it actually sets this lamp on. How many times you do it doesn't really matter. This lamp will still be on. And reversely, if J equals 0 and K equals 1, then if we press this button, then this lamp is going to turn on. This will turn off now. So no matter how many times you do it, again, it doesn't really matter. However, the special case happens when J equals K equals 1. Then when we trigger the clock, then you can see we alternate it, and press it again, we alternate again. So it basically toggles. Alright. Now, besides of using just torches, repeaters, and redstone dust on achieving a JK flip-flop, we have new technologies like droppers and observers, so we can just build one based on that. So here's one. This is just a dropper loop that loops like this. Sorry. And then we have a comparator just reading from this item here. So this is J, this is K, this is clock. So if both J and K are set to 0, then this does absolutely nothing since none of the droppers are powered, because the blocks are not here even, you can see. But if we set J equals 1, K equals 0, then when we try to clock it, then you can see this is set to 1. And no matter how many times we do it, this is still set until we do something regarding J and K. So when J is 0 and K is 1, then we will always reset it. And no matter how many times, it will still be reset. But then when J equals K equals 1, then you can see turns on, turns off, turns on, turns off, turns on, turns off. There you go. Right. So let's just see what interesting things that JK flip-flop brings to us. Now, I haven't really mentioned SR flip-flops. That's because JK flip-flop is literally an SR flip-flop. Why? Because if we say this as a set, this as reset, then set, it sets that lamp, and press it again does nothing. And if we try to reset, then it resets that lamp, and resets, does nothing. So yeah, it already does everything it needs to do with an SR flip-flop. However, there is also an exclusive thing that JK flip-flop does, is that when J equals K equals 1, or when S equals R equals 1, normally this is prohibited for any SR latches and SR flip-flops. However, for JK flip-flops, it basically responds as if it's doing a toggle, like a T flip-flop. So it just have a special defined case when J equals K equals 1, or S equals R equals 1, I should say. That's the first property. The second property is that if we try to connect J equals the complement of K, which basically means when J equals 0, K would equal 1, and when J equals 1, K would equal to 0. So when J equals K complement equals D, what will happen is that it is essentially a D flip-flop. Why? Because we can connect this with a circuit, we just name the circuit D, then this will turn on, and how many times you do it doesn't really matter until we do this, and then it will just set this to off. So yeah, like when you have this complemented, these two inputs complemented, then it's essentially a D flip-flop. We can always just testify it. So if J equals 1, so J equals 1 and K equals 0, so we will have D equals 1. Then if we press it, you can see these lamps turn on, and how many times we press this button, it doesn't really matter. And then when j equals 0 and k equals 1, which represents d is 0, then when we press it, it will reset it. So how many times we press it doesn't really matter. So both of them are 0. So you can already see that jk flip-flop is a d flip-flop when j equals k complement equals d. And lastly, jk flip-flop is itself a t flip-flop when j equals k equals t. Why? Because when j equals k equals 0, then the t flip-flop should do absolutely nothing because it's not supposed to toggle when t equals 0. But then when j equals k equals t equals 1, then it should toggle every time we trigger the clock. That's what it does for a t flip-flop, right? So yeah, jk flip-flop is a t flip-flop when j equals k equals t. So what do we conclude here? Basically, jk flip-flop is a free flip-flop in one. So that's why people call a jk flip-flop as a universal flip-flop, because it can do all the things it can do with an SR flip-flop, with a D flip-flop, and with a T flip-flop. And that's the amazing thing about a jk flip-flop. Alright, so hopefully you'll see the amazing thing about jk flip-flop. And now I've promised you that I would talk about the alternative definition earlier for latches and flip-flops, so I'll just explain it to you now. So if you remember the definitions for edge triggered and edge triggered and level triggered, then we can talk about the alternative definition now. Is that if the latch circuit has a clock circuit, or a clock input I should say, then latches would have level triggered clock inputs, whereas flip-flops will have an edge triggered clock input. Otherwise, if it doesn't have a clock input, then it is a latch, basically. What this is saying is that we are defining latches and flip-flops based on if the clock input is a level triggered or an edge triggered clock input. If it's a level triggered, then it's a latch. If it's edge triggered, it's a flip-flop. This is also the reason why, if we look back at this high level triggered D flip-flop, if we use this alternative definition instead, then we should consider this as a D latch, because it is high level triggered instead of rising edge triggered like this one. So yeah. And in exercise 9.2, I also said it as a D flip-flop, but if you use the alternative definition, then you should call it as a D latch. That's the difference. Why do I introduce you these two definitions then? As I've already said, the definition I have used throughout this video is based on historical reasons, and it's basically just taken from lecture notes from university courses. And yeah, based on that, I just used this definition to here instead. However, there are some modernized versions for the definitions of latches and flip-flops that you might need to use in your applications when you're browsing different online platforms and videos. And you would see the alternative definition used instead. So knowing both definitions help you, because you need to reconcile between the definition I've introduced you earlier and the definition I introduced you now. So yeah, understanding the alternative definition helps you to read through online resources, basically. And speaking of resources, let me just talk to you about the useful resources I've included in the documents along with the work download, basically. They're all in the description below. So the useful resource, the first one I have for you is actually all of the truth tables for the logic gates, latches, and flip-flops I have throughout this video. So I've included a lot of them, so you can just check the truth table out. It's important for you to know how to read truth tables as well, because sometimes when we create logical circuits, we want to see if it matches with the truth table, and if it does not match, it's basically a bug. We need to debug it. And we want to make sure that our logic circuits are correct and display what we want to display correctly. The second resource I have for you is basically the wiki page that I've been referring to for this video, which is Minecraft Wiki's Redstone Circuits memory page. It has a lot of the exact circuits that I've introduced you here, but then in this video I would be able to explain you more thoroughly. So you should check that out. And just be aware, the Minecraft wiki page uses the alternative definition, not the definition that I've introduced you in earlier stage. So make sure that you know the differences between the definition I've used and the alternative definition. The third resource is the Logical Redstone series by MapBatWings. It gives you a beginner depth of creating logical circuits, so it has some additional things that you can learn. For example, you can do addition, subtraction from logical circuits. You can do encoders, decoders. He will teach you the basics of logical redstone, basically, because I would not dive through the logical redstone aspects because I'm expertise in piston doors. So logical redstone is not my professional aspect. So I'll just leave this to other people that you would find more professional knowledge in them. And yeah, all of them are in the document. You can download it from the description below, or you can just view it from the description below. But yeah, anyway, so I would now move on to the exercises. There are only 3 of them for this time. The first one is the one that I've hidden from you, which is actually another type of exclusive OR gate, but then you only use solid blocks, redstone dust, and redstone torches to build them. So I have some hints for you. So A, exclusive OR B, you can just see the relationships between them, and I've also given you the relationship between X and Y. So basically not X or not Y. So yeah, build it within the space, hopefully. And then the second one is this. Using only these components, you want to build a logical circuit with this condition. So the data line should be when open parentheses X and Y, close parentheses, exclusive OR Z, and you want to have a high level trigger D flip-flop between the data line and the clock line. So XYZ represents these 3 inputs, and the clock input is this one. So you can see I set it as a high level trigger D flip-flop, where if you have the alternative definition, then you would say it as a D latch. So, and then also I have some hints, is that it's just a truth table for you. So you can just see if your implementation is correct for the X, Y, and Z. So yeah. The third one is simply a combination lock. Is that you want to have the button to turn on the lamp only when levers A, C, and E are flicked. Otherwise, you don't want to have the button to turn on the lamp. So the data line basically should be A and not B, and C and not D and E, and it connects the data line and the button via an AND gate. So yeah, that's basically it for the 3 exercises. Good luck on them. I hope you learned something from the exercises as well as the entire video as well. And just a general tip for you when you're doing these exercises. I think some of you might be a bit more confused, or you might struggle with fitting your circuit within the space. That's okay, actually. Try to build a circuit away from this, and try to compact it as much as possible until you can fit it into the circuit. So it doesn't matter if your first few attempts are larger than the provided space here. As long as you can achieve this in the final stage, then you're perfectly fine. So yeah, that's basically the tips that I'll give you for you. So this should be a quite a long video, but anyways, thank you for sitting here with me. So thank you for watching, and I'll see you in 1-7 not 1-7 1-10 signal transmission methods and basic miscellaneous circuits. So yeah, stay tuned.